Welcome to the lesson on applications of collaborative robots. Upon completion of this lesson, learners will be able to describe some of the applications of collaborative robots and identify the benefits of collaborative robot implementation based on a case study. As discussed in the previous lesson, collaborative robots or cobots are robots designed to work safely alongside humans in shared workspaces. They typically feature advanced sensors and force-limiting capabilities that allow them to detect and respond to human presence while performing the required tasks. Some of the main applications of collaborative robots include machine tending, pack and place, component assembly, and quality testing. Let us look at the first application, machine tending. So, what is machine tending? Machine tending is the process of loading and unloading parts or materials into machines, typically as part of manufacturing and production operations. In this process, either a robot or human operator places raw materials into a machine, such as a CNC machine. The operator or robot then oversees the machine's operation to ensure everything runs smoothly. Once the machining process is complete, they remove the finished part from the machine. Machine tending has become one of the most popular applications in manufacturing automation due to its ability to streamline production processes and reduce manual labor requirements. In machine tending applications, the robot is responsible for handling various repetitive tasks throughout the production process. The robot loads raw materials into the manufacturing machines. During operation, it monitors the machine's performance to ensure proper functioning. Once the manufacturing process is complete, the robot removes the finished parts from the machine. The robot also performs basic quality inspection of the manufactured parts to ensure they meet specifications. It also handles the movement of parts between multiple machines when sequential operations are required. The robot manages the organization of finished products by stacking or arranging them in designated areas. Let us look at some of the benefits of machine tending in manufacturing operations. By automating the loading and unloading process, it significantly decreases non-value-added work that would otherwise be performed by human operators. The robotic system can perform these repetitive tasks endlessly without fatigue, maintaining consistent performance throughout production shifts. This automation leads to increased production capacity as the robot can operate continuously with minimal downtime. The implementation of machine tending systems is relatively straightforward, requiring minimal programming effort to set up and operate. The precision and reliability of robotic systems help reduce human errors that could occur during manual loading and unloading operations, leading to improved product quality and reduced waste. The next application where cobots are utilized is picking and placing tasks. So, what is pick and place? Pick and place is a process that involves the robot moving objects from one area of its workspace to another. This application is fundamental in many manufacturing and logistics operations. The robot identifies, grasps, and transfers items between designated locations in its work envelope. The pick and place operation performs optimally when dealing with well-ordered objects that have similar shapes and sizes. This standardization helps simplify the programming and ensures reliable operation. Pick-and-place applications are generally easier to implement compared to machine tending tasks. The simpler programming requirements and more straightforward motion sequences make it an ideal starting point for facilities new to robotic automation. Here's a hypothetical case study of a collaborative robot system implementation from EV manufacturing. An electric vehicle manufacturer faced challenges with manual battery cell placement, creating production bottlenecks and quality inconsistencies. With a target to increase production by 40% within 18 months, they implemented a collaborative robot equipped with a vision system and custom end effector capable of handling multiple cell formats. The design specifications required precise cell placement with a plus or minus 0.1 mm accuracy while maintaining the existing factory footprint. The cobot system needed to seamlessly integrate with current battery testing systems and demonstrate flexibility in handling multiple cell formats. The manufacturer implemented a cobot solution featuring a vision system and custom-designed end effector capable of handling various cell sizes. The system incorporated force-torque sensing for precise insertion and integrated quality inspection during the placement process. The results exceeded expectations, achieving a 45% increase in production rate and 99.9% placement accuracy. The implementation maintained workplace safety with zero incidents, and the system achieved a return on investment in just 14 months. The next cobot application to consider is assembly, which is a process where robots perform tasks such as putting together various components to create the final product. During assembly operations, cobots follow programmed sequences to combine different components into finished products. The robot executes precise movements to fit, join, and secure parts according to the assembly requirements. This automated approach ensures consistent assembly quality and reduces the physical strain on human workers who would otherwise perform these repetitive tasks. Cobots are designed to handle simple to moderate assembly tasks when equipped with appropriate sensors and end effectors. In this collaborative setup, cobots manage the repetitive assembly operations while human workers focus on more complex tasks that require advanced decision-making and dexterity. A key advantage of cobots in assembly is their ability to work safely alongside humans in shared assembly spaces, creating an effective human-robot collaboration environment that could maximize productivity while maintaining workplace safety. Quality testing involves cobots performing repetitive inspection tasks, using sensors and vision systems while collecting data, enabling human operators to focus on complex quality decisions requiring judgment and expertise. Visual inspection utilizes cameras and sensors to detect defects and measure precise dimensions of manufactured parts. In force testing applications, cobots employ force torque sensors to verify assembly integrity through accurate measurements. The robots excel at performing repeatable tests while automatically documenting data for quality control records. This hybrid testing approach allows cobots to handle routine quality checks efficiently, while human operators focus on analyzing more complex quality factors that require advanced judgment and experience. An example of cobots assisting with quality testing in automotive manufacturing is performing standardized force tests on automotive switches. The cobot applies consistent pressure and records precise measurements for each test. While the robot handles these objective, quantifiable measurements, human operators work alongside to conduct subjective quality assessments. The human workers evaluate qualitative aspects such as the feel of the switch operation and analyze sound quality. This division of tasks leverages both the cobot's precision in repetitive measurements and the human's sensory capabilities for qualitative evaluation. In summary, collaborative robots have several applications in modern manufacturing and industrial settings. These robotic arms are engineered to operate safely in shared workspaces with human workers, enabling true human-robot collaboration. They excel at machine-tending operations, automating the repetitive work of loading and unloading various equipment. The robots also handle basic pick-and-place tasks, moving objects between locations with precision and consistency. In assembly applications, they support human operators by taking on simple, low-dexterity tasks, allowing workers to focus on more complex aspects of the assembly process. These robots contribute to quality control through integrated sensors and vision systems that perform automated inspections, while human workers retain control over more complex quality decisions. Thank you.